Welcome back to the last session of this meeting on categorical probability and statistics. We have one speaker this afternoon and a discussion session. And the speaker is Prakash Panangaden, who is a very well-known figure in this community. Prakash, before you start, do you like to take questions during your talk or after the talk?
What works best for me is if they post questions in the chat and the session chair keeps an eye on the chat. And if there's some pressing question, like they can't understand what I'm saying and need something immediately clarified, then you should interrupt me. But I won't be looking at the chat all the time. Otherwise I'll be too distracted. But
Sure.
Sometimes there's a lot of background chatter about what did he mean? And then somebody answers and then it's okay. But if there's something that really doesn't make sense, then you should stop me. But yeah, no, and I'm perfectly happy with that.
Yeah, but I understand not for very minor things.
Right.
Okay, so please go ahead. You have roughly 45 minutes and then we still have some time for questions for you.
Great. Thank you very much, Bart, for introducing me. And thanks very much to the organizers, Tobias, Rory, and Paolo, for inviting me to talk at this workshop. It's really remarkable that in this that one of the minor beneficial side effects of COVID is that you can now actually attend multiple things that are supposed to have happened in different places in the world. So originally I was supposed to be in Paris this week and would have had to miss this extremely interesting workshop, but there we are. Now we can go to all these things from our living rooms. So what I'd like to talk about today is somewhat of a continuation of a talk that I gave at the Applied Category Theory seminar 2 months ago in April, on a functorial view of conditional expectation. And of course, I don't expect that everybody in this audience has seen that previous talk, so I'll have to review rather quickly. And I realized when I was rehearsing this talk that review takes up 2/3 of the time for this talk. But nevertheless, I will do that, but then I will push forward and say something about how we used that conditional expectation construction to approximate Markov processes, and in particular, how approximation and bisimulation are closely related in this sense. Okay, good. So, whoops. So the outline of the talk is like this. There's a quick introduction. Then I'll discuss some background, mainly notation. And then I'll talk about cones and duality. And finally, I'll talk about conditional expectation. All of this is essentially a review of what I said in my talk in April, which is fortunately available on YouTube. It is unfortunately, because it's compressed, it's not a completely lossless compression. So it will be perhaps not as clear as the original talk was. But then I start some new material, which is I'll talk about Markov processes from the point of view of expectation value transformers rather than as state transformers. And then I'll talk about how bisimulation enters the picture here. And finally, I'll conclude by what's perhaps a preview of a third talk if somebody invites me to give a third talk on how we use these things. And that will be my concluding slide. Okay, so as I said before, this is joint work with my former master's student, Philippe Chaput, Vincent Danos, and Gordon Plotkin. This was a paper that appeared 6 years ago now in JACM, and the conference version is over a decade old. So sometimes people always want to talk about their latest work, but sometimes after 10 years at least, the old work is forgotten, so you can recycle it. But I still think this work is of interest, because certainly when I gave the talk in April, several people had said they'd never heard of this before. So the conceptual picture is that one should approximate Markov processes by some kind of averaging. Typically what one does when one is approximating a Markov process is that you say, okay, I'm going to take a whole bunch of states in the state space and clump them together. Lump them is perhaps the word that one uses in queuing theory. And then the transitions between these lumps are obtained by averaging the transition probabilities of all the points in a particular lump. So that's the idea here. So these averages, of course, are precisely what expectation values compute. And we're going to use this beautiful functorial presentation of expectation value due to Vincent. And one of the nice side effects of this is making bisimulation and approximation live in the same mathematical universe. Okay, so some notation, and let me just compress this screen a bit. Okay, so supposing we have two spaces. The first one is a probability triple x sigma p, and the second is just a measurable space not actually equipped with a measure, y lambda. And if you have a measurable function from x to y, then you can obtain a measure on the space y by doing what's called pushing the measure p forwards along the map f. And the way you do this is you take the inverse image of a measurable set and look at what p would assign to it in the space x. So this measure that you obtain by pushing p onto y through f is written as this m sub f of p, and it's called the image measure of p under f. So the map goes forwards, the inverse image map pulling the measurable sets goes backwards, and then of course the measure goes forwards again. Okay, we'll say that a measure nu is absolutely continuous with respect to another measure mu if for any measurable set a, mu of a being 0 implies that nu of a is 0, and we'll write nu absolutely continuous with respect to mu by using this double inequality notation, which is typically used to mean much smaller than. That's a deceptive notation, in fact, because in no sense is nu actually smaller than mu. It could be that if they both assign a non-zero measure to a set, that mu actually assigns a bigger numerical value as its measure. But if mu says the measure is 0, then nu has to follow suit. The central theorem linking measures like that is this Radon-Nikodym Theorem. So if nu is absolutely continuous with respect to mu, where both of them are finite measures, actually this works more generally for sigma finite measures. So if these are finite measures on a measurable space, then there's a positive measurable function on the space x such that you can obtain the nu measures by simply integrating h with respect to the mu measure. And so one typically thinks of this h as somehow the density of the measure nu with respect to mu, or perhaps one likes to think of it as a kind of a derivative. And this is actually called the Radon-Nikodym derivative. And one actually uses the differential calculus notation for this. Since nu is finite, this measurable function is actually going to be mu integrable. So this notation L1 plus x mu, which I'm going to introduce later, simply says the set of mu integrable functions that are almost everywhere positive. Uniqueness, as is usual in measure theory, true up to a set of mu measures 0. So if I have an integrable function f and a measure p, I'm going to write f dot p for the measure that has that has f as its density with respect to the measure p. And then two identities that we immediately get are basically, if I use the Radon-Nikodym derivative as the density, then indeed what measure I get by doing that is, of course, the Q measure that I started with. And furthermore, if I take any function f, use it to define a measure through using it f as the density, and then take the Radon-Nikodym derivative of the resulting measure, I will of course get back f. So taking Radon-Nikodym derivative and using a function as the density are just inverse operations. Okay. And they provide maps between the space of integrable almost everywhere positive functions, L1 plus xp, and a space of measures, which I'm going to denote as m with a superscript, absolutely continuous with respect to p. And this is simply the space of finite measures on x that are absolutely continuous with respect to p. So p is in this absolutely continuous sense, bounding the measures in this collection. And this space of measures and this space of functions actually turns out to be very closely related. In fact, in some sense that I'm going to describe in a minute, actually isomorphic. Now, let's say a little bit about expectation and conditional expectation. So if you take a function and on a space that is equipped with a measure, then the integral of that function with respect to the measure is just a number, and it's called the expectation value of f. So the conditional expectation is what you will get if you have additional information. And it's not a mere number, but in fact a random variable. And it is meant to measure the expected value that you compute when you have additional information than just knowing f and p. So this additional information in its most general setting takes the form of a sub-sigma algebra, say lambda of sigma. The experimenter knows for every measurable set B in the sub-sigma algebra lambda, whether the outcome is in B or not. Now lambda might be extremely small. It might just be B complement, and the empty set in the whole space. That's a very, very small sigma algebra. And of course, in that case, this reduces to the traditional notion of conditional expectation given B. But here you can say, it's not just given one set. I'm giving you a whole sigma algebra of sets, not the whole sigma algebra, but some sub-sigma algebra of the whole sigma algebra. And for each of those sets, I'm telling you things about whether the outcome is in that set or not. And now you get to recompute your expectation values. And this is what conditional expectation does for you. So to formalize this, we actually just use the Radon-Nikodym theorem to show that such conditional expectations exist. It was defined like this by Kolmogorov, who said that if you have a measure space with a finite measure and a measurable function integrable with respect to p, and you have a sub-sigma algebra lambda, then there exists a G that's L1, that's in L1, i.e. integrable, such that if you want to know the expectation value of f computed over the set P, you can do it by integrating with respect to G rather than with respect to f. Now you look at this formula and you say, this is a silly theorem. Why can't G just be f? But if you look closely, you will see that G is actually required to be lambda measurable rather than sigma measurable. And if lambda is a much smaller sigma algebra, then in some sense, G is much smoother than f, because it only sees the variations that are visible to the sigma algebra lambda and not to the perhaps much finer sigma algebra sigma. So being sigma measurable means you can be much wilder than being lambda measurable. So what Kolmogorov is saying is that if you want to take a cruder view by looking at this much cruder sigma algebra, you can get kind of a lambda smoothed out version of that conditional, of that expectation value. So this function G is what's typically denoted by this notation, the conditional expectation of f given the sub-sigma algebra lambda. And so in terms of the notations we introduced before, it's clearly just the Radon-Nikodym derivative of f dot p with respect to p, except that now I'm thinking of p as restricted to the sub-sigma algebra lambda. So the properties of conditional expectation is that it smooths out variations that are too rapid to show up in lambda. It is linear and increasing with respect to the point-wise order, and is defined p almost everywhere. So now I want to tell you something about cones, which is the setting in which we functorialized this concept of conditional expectation. Now cones are there to combine linear structure or vector space structure with order. So if you have a vector space with an order, we have a natural notion of positive and negative vectors. And of course, we are simply saying x being greater than the 0 vector is what is meant by a positive vector. So I'll actually say greater than or equal to. So what properties do positive vectors have? We're going to include 0 as a positive vector. So they're closed under multiplication by positive reals, not by arbitrary reals. They're closed under addition. And if a vector and its negation are both positive, then that can only happen if the vector in question is the 0 vector. So this actually defines a cone. So you can define a cone to be exactly a subset of a vector space with these closure conditions. And there's a nice correspondence between having a cone and having an order structure. So as soon as you have an order structure, you can define a cone by taking the positive vectors. As soon as you have a cone, you can define an order by saying u is less than v if v minus u is in the cone. So unfortunately for us, many of the structures that we want to look at are cones. I'm not sure why I said unfortunately. Maybe because cones are perhaps less familiar than vector spaces. So for example, the collection of measures on a space is not in any obvious sense a vector space. Now you can embed it in a vector space by introducing signed measures, but I prefer not to do that. Other people are not so squeamish, and they happily look at vector spaces equipped with order structure or indeed even lattice structure, and they develop the theory quite comfortably that way as well. The cones that arise in our work, and I'm afraid this has to be a very Reader's Digest version of the talk I gave in April. But anyway, let me proceed. The cones that we use are as follows. So if you have a measure on a space X, mu, then one has the usual well-known Banach spaces L1 and L infinity. And these can be restricted to cones by considering the things that are mu almost everywhere positive functions. So this means, well, positive except on a set of mu measure 0. So I'll use a little plus symbol to denote these cones. So L1 plus is L1 functions, except I'm taking only the almost everywhere positive ones, and analogously for L infinity plus. These are complete normed cones. And here again, I'm sorry for the Reader's Digest version, but roughly speaking, they can be given a norm, and they can be shown to be complete in the norm, in the metric induced by the norm. They can also be shown to have an order structure, which comes naturally when you have cones, and certain directed sets. If you have a bounded directed set, then soups will also exist, and the norm limits and the soups actually behave nicely. So, so that's what I mean by complete normed cones. So if you have a measure space with finite measure P, and we look at this space of the cone of all measures that are absolutely continuous with respect to P, we get a complete normed cone. The norm that we introduce is simply the total mass of the whole space. So in such a way, it's an omega complete norm cone, which means countable chains, countable bounded directed sets or countable bounded chains have soups, and these would coincide with the norm limit as well. So I'll use this notation omega CC for omega complete normed cones. These two cones that I've talked about, M absolutely bounded by P and L1 plus, are actually isometrically isomorphic in this category of omega complete normed cones. And there's another isomorphism that you can get. So instead of being bounded in the sense of absolute continuity by P, you can have uniformly bounded by P. So this means that there's some multiple, some real positive real number K, such that the Q measures assigned to sets is always bounded above by K times P. So these are the measures that are uniformly bounded by P, and this gives you another omega complete normed cone. And we get another isomorphism between L infinity plus and these uniformly bounded families of measures. These correspondences allow you to define a nice pairing function. So if you take the product of the L infinity plus cone and the L1 plus cone, you get a nice pairing function that just says, hey, multiply the functions and integrate with respect to P. And this gives you a function that actually mediates the dualities in a nice way. So this map is bilinear, continuous, and in fact, omega continuous in both arguments. We refer to it as the pairing. And it's very important that in addition to the normal norm continuous notion, we have this kind of Scott continuous aspect to it, which gives us a stronger result than what one normally sees in functional analysis. So this pairing allows one to express dualities in a very convenient way. So for their example, there's an isomorphism between L infinity plus and the dual of L1 plus. And it is exactly the one given by this formula, which is of course mediated just by the pairing map. So we get a nice diagram of different spaces of cones and isomorphisms and dualities between them. So the horizontal lines are just isos in both the rows, and the vertical dotted lines are showing you the dualities. So this one is telling you L infinity plus is dual to L1 plus, and of course it's reversed if you look at the dual spaces. This is an interesting thing because in ordinary functional analysis, this is simply not true. The dual of L1 is indeed L infinity, but the dual of L infinity is not usually L1. In this setting, we get it because we have this stronger topological requirement of Scott continuity. So there is a map that I talked about before, the pairing map, which actually mediates all these dualities. Okay, so now let's look at conditional expectation functorially. And we will define two categories, which we'll call rad infinity and rad 1. This is supposed to suggest Radon-Nikodym, that will be needed for the functorial definition of conditional expectation. This will actually allow for L infinity and L1 versions of the theory. And in my April talk, I talked about both of them roughly equally. But here, since they are so symmetric, I will only emphasize one and perhaps only glancingly mention the other. So if you want to go between these versions of the duality, if you want to go between these versions of the theory, duality is a very useful tool. So let me tell you the two categories that we're going to use to define the conditional expectation functor. So on the one hand, we have a category called rad infinity. So the objects are probability spaces, and the arrows are measurable maps such that when you look at the image measure under the map alpha of the measure P that's on the space X, then it is uniformly bounded by the measure in the target space. The reason for choosing the name rad infinity is that if you take one of these morphisms and then you look at the Radon-Nikodym derivative of the image measure with respect to Q, then you get a bounded function, which is of course what you expect from the definition of these uniformly bounded measures. The other category has as objects probability spaces as before, but now the requirement on the arrows is that if you look at the image measure, it's absolutely continuous with respect to Q rather than uniformly bounded. And now, of course, if you look at the Radon-Nikodym derivative of the image measure, you will get something that is integrable, as the Radon-Nikodym theorem told us. So the reason for choosing the name rad1 is that if you take a morphism in rad1, then this Radon-Nikodym derivative function lives in L1. So the fact that the category rad infinity actually embeds in rad1 reflects the fact that L infinity plus embeds in L1 plus. And the pairing function, which is obviously so important in my mind that I chose to mention it 3 times, is the thing that allows us to write explicitly what these isomorphisms are between, for example, L1 plus, L infinity plus and L1 plus dualized. So supposing you have a morphism alpha and rad infinity, so this naturally gives you by precomposition a map from L1 plus y to L1 plus x, obviously in the contra direction since it's precomposition. I put a little subscript 1 on the precomposition functor just to emphasize that it's actually happening in between L1 spaces. Confusingly, you apply it to a map in rad infinity. Similarly, you take a map alpha in rad1, and what it does is with precomposition, it moves maps in L infinity plus to maps in L infinity plus of x. So these precomposition functors are of course simple contravariant functors. So the subscripts on the 2 precomposition functors are telling you what the target categories are of this functor. Now if you use duality, so you get a map now P1 alpha is dualized, and this now, because you've got 2 contravariants composed, it's now going back in the same covariant direction. And it works both in the L1 case and the L infinity case. So the way we're going to define the expectation value functor, so E infinity is going to go from rad infinity to omega complete normed cones. And on objects, it just takes this probability triple to the cone of essentially bounded functions on X. Almost everywhere positive, essentially bounded functions on X. On maps, here's what it does. The action of the functor is to produce a map from L infinity X plus to L infinity Y. And this essentially obtained by composing the dual of the precomposition with the isomorphisms that take you between these 2 spaces. So of course, when people describe things like this, they're absolutely incomprehensible. And it's much more perspicuous to look at the commutative diagram or follow the morphisms along. So I want to define E infinity, the expectation value functor, which takes an L infinity plus function here and gives you an L infinity function down in Y. And the way I do it is I first use the duality to go to L1 plus star, then P1 alpha dualized takes me to L1 plus star of YQ, and then finally the pairing induced duality takes me back to L infinity plus YQ. And that is how we define the expectation value functor. So
sorry, I have a small question about that last diagram. When
sure.
so E infinity, that's the expectation, correct?
Yes.
And how is that diagram related to the fact that the expectation is a right inverse of the pullback map, the P of alpha that you described? Is there a relationship there? Right, because expectations have this property that if you compute the I can't remember the order. I always get confused which one you do first and then the other. But the point is you get back the thing you started with in one direction.
Yes, and I think that is roughly what this formula on the next page is saying, no?
Yes.
Yes, yeah. That is exactly this formula. Which, I think you were there in April, so I talked about this one at length. Actually, I think even proved this, and I got a lot of flack for calling it a left adjoint, but it is indeed better to call it as you did an inverse. And yeah, okay, so thanks. To actually prove this, you just have to follow the diagram around. There's no deep math. It's almost type checking that verifies this formula. Okay. Note that since we started with something in rad infinity, we'll get the expectation value as a map between the L infinity cones. And absolutely analogous story works for the other one. So you can get an E1 functor defined analogously, which I'm just going to skate over because it's so symmetrical. Sorry. But the same kind of equation that Artur was interested holds, except that the positions are reversed. But yes, you can also prove an analogous equation for the E1K version. Okay, so that kind of wraps up the functorial picture of how expectation value works. Let's now talk about Markov processes. And if I am right in my estimation, I have like 18 minutes or so to do that. So normally one thinks of a Markov process as given by a Markov kernel, and what happens is that you are given a point and a measurable set, and you have the transition probability of going from a point to a measurable set. So in this formula here, if you focus on tau, you see it takes a point and a measurable set in its second argument to which it assigns a number. In short, for each x, it's a measure. This Markov kernel tells you the transition probability of jumping from a point x to a measurable set. Now, once you have such a thing, you can view a Markov kernel as actually a transformer of functions. So if I have a function in L plus y, we can define this transformer of f that says just integrate f with respect to this, with respect to the measure induced by the kernel. So this map is well-defined, linear, and continuous. So if you take the indicator function and you ask, for example, what happens if I apply this map to the indicator function, I get back exactly the kernel that I had started with. So it tells me this is the transition probability of jumping from the point x to the measurable set p. So it encodes all the transition probability information. And in some sense, this is like going from the state transformer view to the predicate transformer view of what a transition system is. So the state transformer view is exactly what's given here. You give a point and you ask, where are you after a jump? Here it says, I'm going backwards in terms of the expectation values of functions. So given any omega continuous morphism L satisfying this inequality, it can be expressed as a Markov kernel essentially by reversing the process on the last slide. There's actually a non-trivial piece of functional analysis to prove that, which I'm kind of skating over. But the point is, I'm now thinking of these Markov kernels and Markov processes not as state transformers, but as expectation value transformers of random variables. So the interpretation of this thing is that applied to the indicator function of a set P, you get a measurable function such that you get the transition probability for each point of jumping from that point into the set P. So we can also define an operator on the measures by using tau the other way. So it's a measure transformer as well, by essentially integrating the first argument with respect to the measure in question. So it transforms the measure mu into a new measure. This is more or less the forward view. It's easy to show that this map is also linear and continuous when you think of it as a cone map. So this tau bar T, which I just introduced as the measure transformer, is the forwards in time picture and tells you how measures transform through transitions. The other one is a likelihood transformer, and it's like in programming languages, what we like to call the predicate transformer semantics. So tau T of f is just the expected value of f after one tau step, given that one is at x. So we're going to define abstract Markov kernels as omega continuous linear maps defined on the cones with the suitable norm condition. This, of course, tells you that these taus are in fact, as maps between Banach spaces, they're continuous. A labeled abstract Markov process on a probability space with a set of labels or actions is a family of these abstract Markov kernels indexed by the elements. So the idea of this labeling is simply that you can imagine a process that has multiple actions that an experimenter may choose to perform. And in response to each of these actions, the system responds by performing a particular transition of a particular Markov process. If there's just one action, it's an old-fashioned Markov kernel. Having multiple labels doesn't do much damage or confusion to the theory. You just have to add a little notation to keep track of them. So I will mostly not talk about labels very much. But now we see where we use conditional expectation to define a kind of modification of the transition kernel. So let's say we have a setup, and let's imagine a transition kernel on the same space. So you're jumping around to different points in the same space. So your transition kernel tau sub a is going from L infinity plus of x back to L infinity plus of x. And it's describing the dynamics of a system in the predicate transformer view. Supposing I have another space, y, and I have this map alpha from x to y, then just as before, I will induce, induce a map like this. So I can define a map alpha of this kernel tau by saying, okay, first I use p infinity alpha precomposition to take me from y to x. Then I perform the transition using the kernel tau, which is defined on x. And then I use the conditional expectation functor to bring me back to the space y. And when I do that, that's the definition of alpha applied to tau a. So what we are thinking of, how we are thinking of this is that we are somehow approximating along the morphism alpha. This may seem a bit weird. So let's look at a special case where the spaces x and y are in fact exactly the same as underlying sets, only the sigma algebras are different. So now we have a morphism ID, which is the identity function on the underlying sets. And since lambda is a subsigma algebra of sigma, in this direction, the map is measurable. So this is what we will call our alpha for this setting. And now if you look at what we've done, what we have done is we've said, okay, I've got this ID function applied to tau alpha, and it's giving me now a map defined on the coarser space. Same point set, but with a coarser sigma algebra lambda defined on it. Same measure, which is just a measure restricted to the subsigma algebra. And so what you see here is that we've taken our transition kernel and we've said we've got a kind of cruder version of it defined with the space equipped with a cruder subsigma algebra. So thus, this is the approximation of tau A obtained by averaging over the sets of the coarser sigma algebra. That's exactly the averaging that E infinity is doing for us. But with this machinery, we can say, hey, why are we just coarsening along these maps, these identity maps with subsigma algebras? We can approximate along arbitrary alphas, and that is what we have done. This is now for any map alpha in our category, we can say, I can think of some notion of approximating a kernel along that map alpha. In some instances like this, it clearly jives with our intuitions about what approximation should mean, but in other cases, it might be more of a stretch to think of that as an approximation, but at least formally, all these things live in the same universe of approximations. So let's look at a very special notion called bisimulation. So traditionally, bisimulation, well, there's always a big argument about who defined bisimulation. I'd like to say Cantor defined it. But so in the queuing theory communities, it was defined in the 60s under the name lumpability. It was defined, of course, in the concurrency community by Milner and Park, and it was defined in the probabilistic setting by Larson and Skow. Of course, in the machine learning world, they think it was defined by people who came much later. Anyway, given a labeled Markov process, an equivalence relation is called a probabilistic bisimulation if for every measurable R closed set, we require that the transition probabilities to that set exactly match for every action. Now, what do I mean by measurable R closed set? So R is already an equivalence relation. So an R closed set is simply a union of equivalence classes, but we're only considering the measurable ones because those are the ones to which we can assign transition probabilities. So this is pretty much the same as the Larson-Skow definition, which was originally defined in the completely discrete setting of finite or countable discrete spaces. José de Arnay and her Indian friends, one of whom is me, extended this to the continuous setting, and we found that all we had to do is to require these R-closed sets to be measurable. Okay, so this is a notion of behavioral similarity. We'll say the two states S and T, they have exactly the same transition probabilities to equivalence classes, and then thereafter, because you're jumping into equivalence classes, they will stay bisimilar. But at some point, we started feeling that if you're really doing this in a measure theoretic way, we should be focusing on measurable sets rather than on points. And so, again, inspired by Vincent Danos, well, not just inspired by, he actually gave this definition. We will define something called an event bisimulation, and this adjective event is supposed to emphasize that we're thinking of the measurable sets rather than the points. So this is just a sub-sigma algebra such that when you look at the transition kernel restricted to lambda, it's still a Markov process. And this means what tau does is it sends the subspace of these functions to itself, where we are now viewing tau A, as I've done before, as a map on the space of random variables or integrable functions. So if you look at it from the point of view of approximation, what's so special about bisimulation? It says, oh, if I look at lambda as a sub-sigma algebra of sigma, and then do the approximation picture that I had before using the standard embedding, then back here I get exactly tau restricted to lambda. In short, what bisimulation is hey, you can approximate along this, but it'll be exactly the same, you won't lose any information. So bisimulation is a special kind of lossless approximation. And it says, okay, if you want to look at this cruder picture, you can do so safely without actually losing anything. So let me give a more general notion of how we define bisimulation here. So I'm going to define an important concept called a zigzag map. All these things were defined in this state-based picture, but I'm doing it now in the expectation value transformer picture. So this is a map from one probability triple to another, and both those triples are actually also equipped with Markov processes. So these Markov kernels, tau and rho respectively, such that the following picture commutes. If you start from the space Y, use precomposition with alpha to go to X, use the kernel to move around in X, it's exactly the same as if you were to stay in Y, do the transition here, and then use precomposition to go to X. So this is saying tau and rho are basically doing more or less the same thing. Okay, so such a map, it's a very strong connection. Such a map, if it exists, is called a zigzag map. So alpha is the zigzag. And if you have a zigzag, then you get a commutative diagram. So if you look at this upper trapezium, it just says that we have a zigzag. This is exactly the definition of a zigzag. The lower thing says, oh, we have an approximation. And over here, the commutativity of this triangle is a lemma that we proved in our paper earlier. So what this whole picture is telling you is that if you approximate along a zigzag, you actually get the exact result. So down here is some kind of generic approximation, but up here, if you see that it's a zigzag, you will get exactly the same result as if you didn't approximate.
Could you kindly remind me, what was alpha a function or a stochastic map in this case?
Alpha is a function. It
Okay.
is a map from x sigma p to y lambda q. Yeah, and it's the kind of thing for which precomposition and expectation value are defined. So you can see there's an expectation value morphism here going from L infinity x to L infinity y, just as I did before. I understand I'm rushing at Bart speed. Okay, so approximations are essentially approximate bisimulations. That's what they are. So just to tie up the story of bisimulation, what zigzags are doing are actually giving you a kind of functional version of bisimulation, but bisimulation is usually thought of as a relation. So use cospans of zigzags. Now, in the general theory of bisimulation, everybody loves to use spans, but we have found that cospans give a smoother and more general theory. So with spans, you can prove a kind of logical characterization theorem of bisimulation, but it requires some restrictions on the spaces. Namely, we require them to be analytic spaces, which, you know, it's a topological restriction and it seems alien to the whole process. But with the cospan definition, we are able to prove logical characterization on all measurable spaces. So this is a significant extension. And you might ask, well, is there a real difference between the spans and the cospans? And the answer is, well, on analytic spaces, the two concepts coincide. No wonder we can give a logical characterization either way, but there are examples showing, so Pedro Teraf has given explicit examples showing that the theory cannot be made to work with spans on general measurable spaces. You have to use the cospan version. And he's given examples showing that the cospan bisimulation and the span bisimulation wouldn't match up in those settings. Okay, so I'm defining the relational picture of bisimulation using these cospans. So here is the official picture. So we'll say two spaces X and Y equipped with the appropriate structures are bisimilar if there is a third space equipped with all the structures such that I can define zigzags alpha and beta pose into Z. Okay, so of course it would be asking too much to get a zigzag directly from X to Y. If you have that, they're certainly bisimilar, but more generally, you can require a cospan. So the identity, by the way, is always a zigzag. So if you do have a direct zigzag, it immediately fits this definition as well. So the fundamental point, which required some work, nothing terribly exciting, but you have to do the work, is that the category of these abstract Markov processes with zigzag morphisms, well, with simulation morphisms, has pushouts. But if the morphisms in the span are zigzags, then the morphisms in the pushout diagram are also zigzags. And with that in place, you can now give the satisfactory definition, or you can tie up the definition of bisimulation as being an equivalence by essentially using the pushout to show that you have transitivity, because of course composing zigzags gives you zigzags. And the pushout of these two zigzags are also zigzags, so everything works nicely. And thus we have that bisimulation defined this way is transitive. So to summarize what we have done, we've analyzed this notion of bisimulation in this predicate transformer version of the theory, and we have tied it up with the notion of approximation and shown that bisimulations are a special kind of lossless approximation. So approximation and bisimulation live in the same universe. So just to wrap up in the last slide. So what did we do with all this? Well, we were able to prove logical characterization of bisimulation for any measurable space. But the most important thing is that we developed a theory of approximation by looking at finitely generated subsigma algebras coming from the logic. And so these were all, of course, approximate bisimulations. So we could look at all these approximations, and we were able to show that there is a canonical minimal realization of any Markov process. And furthermore, this arises as the projective limit of the finite approximations. So a logical characterization result, an approximation construction, and a minimal realization result, and also the fact that the minimal realization is obtained by taking the limit precisely of these approximations. So this, maybe one day somebody will invite me to give a third talk, in which case I can talk about these things. But anyway, I'll stop there. I know Bart is the toughest chairman around, so I dare not exceed my time limit. Thank you.
Thanks a lot, Prakash. Let's all unmute and applaud for Prakash. Thank you very much. I saw on chat, Arthur, that you have a question.
Yes. By the way, thank you very much for the talk. So I have sort of a, this is maybe a naive question, but I guess.
Let me guess. You want to ask me about quantum versions?
No. Something much more basic. I guess. Why are we not working with actual Markov kernels? And I was wondering if it's because, like, why are we working with the L-infinity spaces? And is it because a map of L-infinity spaces need not come from an actual Markov kernel on the underlying space?
So we actually did do all this theory earlier on the actual Markov processes, or what you're calling the actual Markov processes. So in some sense, this whole paper was redoing all those things in this other setting. So both things can indeed be done.
Okay, so there's not like some measurable, restrictions like that you have to assume, like special kind of spaces that you're working with necessarily, or
in the Markov process world, we had to restrict to analytic spaces to get most of our results.
But you did
the notion of event bisimulation, some of the results were pushed to general measure spaces, but we didn't really work out how to do approximation without this analytic space restriction.
I see. And you were able to remove that restriction by working with the associated L-infinity spaces instead.
Yes.
Okay, excellent. Thank you.
Is there another question?
I can see Gordon Plotkin's curtains, but not his actual face. Oh, hi, Gordon.
You have a question? I can't see Gordon, but please speak up if you have a question. Or report so in the chat. While we're waiting, Prakash?
No, I don't have a question, just curtains, sorry.
Okay. Prakash, in the old work of Dijkstra in this area, there is a bijective correspondence between computations and predicate transformers, and in that setting that's called healthiness. Is that also essentially what you're proving in this setting?
Yeah, so I'm not 100, no, I should say I don't know, because I remember the word healthiness, but I don't remember what the technical condition was. But I think we're proving something like that. I mean, something like that must be true for all this to work out like this.
Yeah, so one way you can formulate it, if you take a Kleisli map for the power set monad, so that's a non-deterministic computation, that's in bijective correspondence with I can't remember precisely, a supremum preserving map between the corresponding lattices, complete lattices of predicates.
Right. This is probably something Gordon and Mike Smith proved, or Gordon alone. I don't know.
Oh, okay. Well, anyway, I wasn't claiming that Dijkstra was actually proving this. Just the fact that it holds in that setting, and there it's called healthiness.
Mm-hmm.
But so part of what you're doing is moving things that people would normally do at the level of computations to the level of predicate transformers.
Yes.
That's correct?
That's exactly what we're doing, yes.
Yeah, yeah. And the question then is, to what extent would that generalize to other settings? Or to what extent, this is a rather vague open question, is it really specific to the probabilistic setting in which you're working?
Is this an invitation to praise you, Bart?
No.
Well, so everything we did is very specific to probability, but of course, I'm well aware of your work, which gives a much more general setting for this predicate transformer, state transformer, those triangles that you were so fond of. So at least I know through your work that analogous things hold in the quantum realm. And certainly from, classical results, we know that these things work for non-deterministic computation.
Yeah.
And I imagine now that I've seen, using undergraduate induction, if it works 3 times, it always works. So I think this is probably a very general thing.
Yeah.
But everything we did was very, very measure specific, and we got, down and dirty into details of measure theory to get things to work. I don't know if there's, there's this idea that analysts are Morlocks and categorists are Eloi. I don't know if people get this reference. This is from The Time Machine, where the Eloi were these people who wore light skirts and flowers in their hair and were dancing all around outside, and analysts, or the Morlocks were these people who lived in these underground caves. And occasionally they ate the Eloi. But anyway, I don't know if there's some beautiful, totally abstract, pain-free proof that works in general. I kind of doubt it, because every time categorists have told me, yes, this is all going to work from general reasons, and every time I've tried to do it, there is always some pain that they didn't warn me about. So I don't know if there's a pain-free path to proving these kinds of things.
No, I'm asking because I'm very much interested in avoiding the pain that I see in this work. Yeah.
Pain is good for you, Bart.
I was not looking for praise. No, don't get me wrong. Any other question here? Okay, well then let's thank Prakash again, and we will think about a third opportunity, Prakash, to invite you and give you the opportunity to finish this trilogy.
Yes. The return of the Markov process, we'll call it.
Yeah. Thanks again.
You're welcome.